Hello everyone. In this video, we introduce our latest work, DGVO, a dynamically constrained gradient velocity obstacle approach for mobile robots in dynamic environments. Our motivation was to enable robots with non-holonomic constraints to safely and robustly navigate in complex dynamic obstacle environments, which is challenging due to the shortcomings of existing methods. To address this, we proposed the velocity feasible region and integrated it with the VO framework, establishing an unconstrained optimization framework called Dynamically Constrained Gradient Velocity Obstacle, DGVO. Through nonlinear mapping based on the robot's kinematic model and input constraints, we obtain the velocity feasible domain of the non-holonomic constrained robot, combine it with the VO region to get the safe velocity region, SVR, grid the SVR, and transform it using SDF to obtain DGVO. With DGVO, the robot's optimal obstacle, avoidance speed in complex dynamic environments can be calculated in real time and efficiently. Based on this, we established an obstacle avoidance framework with modules like positioning and perception and completed relevant experiments. In the experimental phase, we began with a simulation experiment on Unity using a differential robot. In the first scenario, 20 obstacles were randomly placed in various directions, creating a complex environment. Our robot successfully navigated past each obstacle and completed the task efficiently. In the second experimental scene, a comparative study was conducted. Our DGVO method outperformed other methods in obstacle avoidance and safely reached the randomly designated endpoint. We then conducted physical experiments on both the Ackermann platform and the differential platform. In the first experimental scene, 3 experimenters moved laterally as obstacles. The robots on both platforms effectively avoided the obstacles. In the second experimental scene, the 3 experimenters walked towards the robot from different directions. With DGVO, our robot demonstrated excellent obstacle avoidance capabilities and successfully completed the task. These experiments demonstrated the effectiveness and reliability of our DGVO method in complex dynamic obstacle environments. Finally, we tested the 2 robot platforms in a real-world corridor at Shanghai, Shenzhen University. Despite different human traffic densities in the 2 experiments, the robots on both platforms performed excellently, avoided the crowd, and safely returned to the endpoint, verifying the effectiveness of our proposed method.